Hi, this is John Whitaker for the Mathematical Analysis class, and this is our 26th video lecture. And today we're going to do a little bit more work on limits, and then we're going to functions. And then we're going to go on to continuity for functions. We ended last time with a theorem being written down. I'm going to start by writing down that theorem and giving the proof of the first part, saying that the other parts follow similarly. And so here was that theorem. Suppose E is a subset of X in metric space. P is a limit point of E. F and G are complex functions on E. And the limit as x goes to P of f of x equals to A, and the limit as x goes to P of g of x equals to B. Then, first part is that the limit as x goes to P of f plus g, we've already defined that new function, is equal to A plus B. Part B, the limit as x goes to P of f minus g acting on x is equal to A minus B. Part C, the limit as x goes to P of f times g acting on x equals to A times B. And finally, the limit as x goes to P of f over g acting on x is equal to A over B, and that's provided B is different from 0. So those are the four statements that we have when we're talking about two complex functions whose limit exists at P. And what we're going to do is prove part A. And the rest of them follow analogously to what we'll do for part A. So I won't do those. And it'll be based on the sequential criteria for function limits. So here's our proof. We'll let E be a subset of X, a metric space. I'm writing the conditions of the theorem, the hypothesis. P be a limit point of E. F and G be complex functions on E, and the limit as x goes to P of f of x, we're going to let that equal to A, and the limit as x goes to P of g of x, that equals to B. So part A, we want to show the limit as x goes to P of f plus g of x equals to A plus B. Okay? So here's what we're going to do. We're going to let P sub E be a sequence in E such that, so we're looking to use the sequential criterion for function limits. So the required type of sequence that we look at in the sequential criterion for function limits are guys in the domain of the function, sequence in the domain of the function, that none of the terms are equal to p, and that the limit as n goes to infinity of p sub n equals to p. Now, what we want to show is that f plus g acting on p sub n will converge to a plus b. But we'll get there because since the limit as x goes to p of f of x equals to a, then by the sequential criterion for function limits, the limit as n goes to infinity of f of p sub n, that will equal to a. Similarly, since the limit as x goes to p of g of x equals to b, then by the sequential criterion for function limits, the limit as n goes to infinity of f of p sub n will be equal to b. Now, we take a look at the limit as n goes to infinity of f plus g acting on p sub n. That's going to be equal to, and what I'm going to use first is the definition of what f plus g is acting on an input value. That's going to be equal to the limit as n goes to infinity of f of Pn plus g of Pn. Now, since both of these converge as complex sequences, then the limit of an addition of complex sequences is equal to what they converge to. So that's equal to, the addition of what they converge to is a plus b. So, by the sequential criterion for function limits, since the limit as n goes to infinity of f plus g of p sub n equals to a plus b, where p sub n was the right type of sequence, something n-y, none of its terms are equal to p, but yet it converges to p. And by the sequential criterion for function limits, the limit as x goes to p of f plus g will equal to a plus b. And that proves part A. And what I want to tell you is that the proof for parts B, C, and D work analogously. They are dependent. And this really isn't the only way to show it, but they are dependent on the sequential criterion for function limits. It's not the only way to prove these parts, but it is a way. That's what the book presents, and it's a good way. That's what I'm presenting too. So for me, that ends this theorem, even though I didn't do the last three parts. It's the same. Next, I want to make a statement. I won't do a proof that has to do with Euclidean space. So here's, I'll call them facts. If F and G map E into RK, P is a limit point of E. The limit as x goes to P of f of x equals to some value in RK, we call it A bar, and the limit as x goes to P of g of x equals to some value in RK, we'll say B bar. Then, the limit as x goes to P of f plus g acting on x will be equal to A bar plus B bar, and this is part A, so I'm saying two facts here. Part B, the limit as x goes to P of f times g acting on x equals to A bar times B bar. Now, what does this times mean? Where the times, the dot, okay, represents the inner product between A and B. That's not something I'm going to prove, but it is a true statement. Instead, I want to move on to continuity. Which is a lot like limits of functions. So here's the definition. Suppose x and y are metric spaces. E is a subset of x. P is an element of E, not a limit point, okay? It might be a limit point, but it's an element of E in this case. And F maps E into Y. Then F is said to be continuous at P. If for each epsilon greater than 0, there exists a delta bigger than 0, such that the distance in Y between f of x and f of p will be less than epsilon whenever, or for all x. What does it say here? It says for all x. For all x in E with, this was in Y, the distance between x and p is less than delta. Now, one thing we don't have here is this being bigger than or equal to being bigger than 0, as we had in the definition of a limit. Okay, So two distinctions between continuity and limits is that for limits, P was a limit point. For continuity, P has to be in the domain space. And then for limits, you had to have the distance between x and P, the input values and P. They had to be bigger than 0. Here we don't have that requirement. There's another difference. Here we had the number q, but in this case we have f of p. So f of p exists. All right, let me give some idea of what we mean by continuity. It's much like what we mean by limits, but a little different. So the idea is f is continuous at p. If the f of x values can be made arbitrarily close to f of p, and that's for all x in E that are arbitrarily close to P. Okay? And that is including P. If we look at a picture, here's what we're thinking. This is x. Maybe this is the set E. And then P is sitting here. And here's Y. And this is f of P, which exists, because P is in E. And here's P. What we're doing is if I take some little region about P, every point in this region is mapped to some close region to f of P. So things very close to P get mapped to things very close to f of P. Let's look at an example or two. So as an example, if we look at f of x is equal to 2 times the square root of x, if x is greater than or equal to 0 and x is different than 1, and let it be equal to 1 if x is equal to 1, let's make that 3, if x is equal to 3, then f of x is not continuous at x equal to 1. And we can see this pictorially. So here's 1, here's 2, 3, 4. 1, 2, 3, 4. When we let x be 0, we get out 0. Square root 0, 0, 2, 0. When we let x be 4, square root of 4 is 2. 2 times 2 is 4. Make that a little higher. And we have this hole here. It would normally be at 1, 1, but it's missing. Instead, it's up here. Okay. So here, if I take
epsilon equal to a half, so I'll go a half above and a half below, f of p, f of 1, which is 3, then no matter how close I get to 1, there's going to be points within that region that aren't within half of the unit of 3, what f of p is. So that's why it's not continuous at 1. Let's look at another example. Let's let f of x be equal to 4x plus 2. And here we're taking e is equal to r, and it goes into r. Okay. And I want to say it's continuous, this function is continuous at x equal to minus 1. Let's look at the proof of this. Okay, so here we're going to start off by letting epsilon be greater than 0 be given. We're going to use the definition company. We need a delta bigger than 0 such that for all x element of E, which is R, such that for all x ending with, here it will be the distance between nx, between x and p is less than delta, then the distance in y, which is still the distance in r here, between f of x and f of p will be less than epsilon. I said this in a generic way, but really we should make it specific to our problem. So that is, we need a delta greater than 0 such that for all xn, it's the real numbers of what it is, with the usual metric here in the real number system, it's going to be the absolute value of x minus, our p is minus 1, so minus 1 is less than delta, then we'd like for this to happen, and that is again y being r. We have the usual metric, that is f of x minus f of minus 1 is less than epsilon. So I'm going to concentrate on this part. So we want to force this to happen, which is the absolute value of f of x, which is 4x plus 2, minus, what is f of minus 1? Well, it's minus 4 plus 2, so that's a minus 2. We want that to be less than epsilon, so that's what we want. I'll work with what we want and see if I can get it in terms of what I can control, which is x minus a minus 1. So we want 4x plus 4 to be less than epsilon. That means we want 4 times x plus 1, inside absolute value to be less than epsilon. That means we want 4 times the absolute value of x minus minus 1 to be less than epsilon. That says we want x minus a minus 1 to be less than epsilon over 4. And so I get to pick a delta such that we have the x minus a minus 1 to be less than whatever delta I pick. And the delta that I want is sitting right there. So we let delta be equal to epsilon over 4. And then I'll just make a conclusionary statement. You work backwards, but for me, this is a good enough, sufficient proof. Then for all x in R with x minus and minus 1 being less than epsilon over 4, if you work backwards, we would get then the absolute value of 4x plus 2 minus minus 2 would be less than epsilon. And so that tells us that f of x equal to 4x plus 2 is continuous at x equal to minus 1. And that's the proof. Now I want to prove a fact about continuity, and it's dealing with the definition we haven't spent a lot of time with, but was given in chapter 2 when we had a long string of definitions, and that was an isolated point. So we'll talk about that in just a second after I get the theorem up. But here's the fact. Let x and y be metric spaces E be a subset of x, F's a function that maps E into y, and let P be an element of E with P being an isolated point. Of E. Really, saying P is in E with P being an isolated point is a little bit redundant. When we say P is an isolated point of E, what that means is P is an element of E, and P is not a limit point of E. And that's what that definition means. Then, F is continuous to P. Before I go to do the proof, let me do an example of an isolated point. If you had A equal to maybe something like 0 to 7 in the real numbers union with 11, then 11 would be an isolated point. Of A. It's isolated in that there's nothing from A besides 11 out there next to 11, close to 11. Okay, well now let's prove this fact. All right, so here's the proof. We let x and y be metric spaces. E be a subset of x, and F maps E into Y, and let P be an isolated point of E. We want to show that F is continuous at P. Okay? So how do we do this? Well, we let epsilon be greater than 0 be given. What we're looking for is a delta. We need a delta bigger than 0 such that for all x in E with the distance in x between x and P when that's less than delta, then that's going to force the distance in y between f of x and f of p to be less than epsilon. So we're looking for this delta. Well, we turn to the isolatedness of p to get a delta. It's usual. So since P is an isolated point, of E, what that means is there exists a neighborhood of P such that, let's call it n sub r, or let's call it n sub delta of P, such that n sub delta of P intersects E, it does intersect, only at P. So the only thing in n sub delta of P that's also in E is P. Okay, so I'll say that again. So, so P is the only x value, if you will, in E with, or satisfying, in using the metric in x, that the distance between x, remember this is the metric space, this is the point in there. X and P, I just changed this book so that that's input value, is less than delta. Okay? So, for all x element of E with its distance from P being less than this particular delta, then the distance in y between f of x and f of p. Okay, well, when we talk about these x's, there's only one, that's p itself, and so the only x we're talking about is p, so f of x is f of p, its distance from f of p is equal to 0, which is definitely less than epsilon. So that tells us f of x is continuous at p. At P. And that is the proof.
So now we want to do another theorem about continuity. So here's the theorem. We're going to let x, y be metric spaces. E be a subset of x. F maps E into y. We're going to let P be an element of E such that P is a limit point. Of E. Okay, look, in E, you only got two types of points. You're either a limit point or you're an isolated point. That's it. Okay. Then, F is continuous at P if and only if the limit as x goes to P of f of x equals to f of P. So we can relate continuity to limits of functions when P is a limit point to P. We need to do the proof. We'll start off by assuming conditions. So we're going to let x, y be metric spaces. E be a subset of x. We'll let P be in E and be a limit point of E. I'm sorry. Okay, so that's the setup. And now going in this direction, we're going to suppose that F is continuous in P. And we want to show that the limit as x goes to P of f of x equals to f of P. That's what we want to show. And so in order to show that, we're going to let epsilon be greater than 0 be given. We need a delta bigger than 0 such that for all x in E with the distance, with 0 less than the distance between x and P is less than delta, then the distance in y between f of x and f of P is less than epsilon. So we're looking for this delta. Well, the delta is going to be generated by the continuity of f at P. So since f is continuous, So since f is continuous at p, and we've been given an epsilon, there exists a delta greater than 0, such that for all x, that's the delta we need, element of E with the distance in x between x and p less than delta, then that forces the distance in the metric space y between f of x and f of p to be less than epsilon. Okay? Now look, we just needed this delta such that when we talk about points in E whose distance from P is less than delta get bigger than 0, we get this result. So we're talking about more x's than what we need to be talking about. So what I'll say is, so for all x in E with 0 less than, the distance between x and P is less than delta, then we have this result. And so that says that the limit as x goes to P of f of x has to be equal to f of p. So it's an if and only if statement we've done part of it. Going in the other direction, we're going to assume that the limit as x goes to P of f of x equals to f of P. We want to show f is continuous at P Okay, how are we going to do that? Okay, the way we're going to do that is that we use the definition of continuity. So on the left, epsilon greater than 0 be given. We need a delta bigger than 0 such that for all x in E with the distance between x and P is less than delta, then that will force the output values, which are in y, their distance from f of P to be less than epsilon. Okay, well, we're assuming the limit property, so since the limit as x goes to P of f of x equals to f of P, there does exist a delta greater than 0 such that for all x element of E with 0 less than the distance between x and P is less than delta, then we get what we're searching for. That is that the distance in y between f of x and f of P is less than epsilon. So look, we want that for every x, such that this happens, then this is the result. What we've got is for every x such that this happens. Well, these two quantities include all the same x's except for one, except possible one. Well, except for one. The one x that's not included is when x is equal to P, and we need for it to be. Now, when x equals to P, okay, well, what is the distance in y between f of x and f of P in this case? Then the distance in y
between f of x and f of p, in this instance, when x is equal to p, is equal to the distance in y between f of p and f of p, which is 0, which is definitely less than epsilon. So that means we had the statement that we wanted for all x's in E such that x was within delta units of p but not equal to p. But even if x is equal to p, we get what we want. So that means for all x in E with the distance between x and p is less than delta, then the distance between f of x and f of p will be less than epsilon. So that says that f is continuous at p, and that concludes this theorem.
Okay.
Well, I have time enough to write up at least the theorem, maybe a little bit more. So I will for the next theorem. It says, let f and g be complex functions on a metric space X. With f and g being continuous at p, now of x. So here's our two parts. Then, part A is that f plus g of x is continuous at p. And part B, f minus g of x is continuous with more than two parts. At p, f times g of x is continuous at p. Part D, f divided by g of x is continuous at p. And that's provided one thing, g of p is different from 0. Okay. Look, based on our previous work, all of these parts work the same. And so I'm going to do part A. So here, here's the proof. We're going to let X be a metric space. Let f and g be complex value functions, that are continuous at p. Just this particular p is an element base. So for part A, we want to show f plus g is continuous at p. So we're going to consider two cases. Okay. So here's case one. Suppose suppose P, now P's an X, suppose P is an isolated point. Of X. Then, automatically, we've shown by a previous theorem f plus g is continuous at X. I'm sorry, at P. Now, case two, suppose P is a limit point of X. Again, we want to show that f plus g is continuous at P. So, since f is continuous at P, then the limit as x goes to P of f of x equals to f of P by a previous result. Similarly, since g is continuous at P, then the limit as x goes to P of f of x, g of x, equals to g of P. These are true because P is a limit point, okay? Complement theorem that we had proven just a few seconds ago. So, the limit as x goes to P of f plus g acting on x is the limit as x goes to P of f of x plus g of x, which by an algebraic property of limits that we had proven, theorem, about complex functions. Okay. That's equal to the limit as x goes to P of f of x plus the limit as x goes to P of g of x, which equals to f of P plus g of P, which equals to f plus g acting on P. We had that theorem as if and only if theorem, so since the limit as x goes to P of f plus g equals to f plus g acting on P, and P is a limit point, that means f plus g is continuous at P. And so that concludes that proof. And the other parts of this theorem, that concludes that. The other parts of this theorem are proven analogously. Okay, so I will consider that to be the end of the proof of this theorem of 4 parts. Ladies and gentlemen, that's more than my time for this lecture. I want to thank you very much for your time and patience.